This is the first of two independent lessons that are intended to be covered while I am absent in a couple of weeks from when I'm actually recording this. This first lesson is on systems of equations by graphing. Now, some of this content should overlap from Algebra 1 and some of it's going to be new, and a lot of it is going to focus on how we can use the features in Desmos to actually make this easier for ourselves. So without further ado, let's get to the lesson. This is intended to take what would be the equivalent of a class period. So you can expect this video and this assignment to be a little bit longer than a video that's just for the lesson component, but does not incorporate practice or homework. Just heads up on that. So we're starting with a key idea. When we graph, we are simply shading in the solutions. So let's go slowly and reflect on that. When we graph in math, what are we doing? We're drawing pictures, but what are we drawing pictures of? We are drawing pictures of solutions. So recall what a solution is. I know I'm on this all the time, this definitions and the vocabulary, and I'm going to be emphasizing that in this video as well. But solutions are the values of the variable. And I might even put an S on that because we're going to start dealing with more than one that make the equation true. And I know recently in teaching, I had that up on the board and I was like pointing at it. And I said, the reason why it's so important for you to understand what a solution is because that never ever changes. That's what we're being asked to find whenever we have the direction solve. Okay, so recall what a solution is. Now, for an example, in one dimension. So in one dimension, all we have is a number line. Okay, that's all we have in one dimension. So one dimension is essentially just the x-axis with no y-axis. That would be two dimensions. And if I were to graph this, I might have like 0, 1, 2, 3, 4. Okay, there's the 3. And what I would do is I would simply put a dot, I color it in at the 3. Okay. Now, I know I've got more on here. Now there's going to be something underneath my head. We don't typically do this in one dimension unless we're graphing inequalities, and that's actually going to be the second of the independent lessons that we have for when I'm out. So we don't usually do that in one dimension. So if you're thinking, Ms. Taylor, that's a little bit weird that you are just plotting a dot on a number line. Yeah, like a little bit weird because we don't usually do it, but that is what we're doing, okay? Is we're just putting a dot at x equals 3. We're putting a dot at wherever the solution is. Now, why is it important for us to think about that and reflect on it? Because math is consistent, and you're going to hear that a lot in this particular lesson as well. Math is consistent, and too many students kind of feel like math isn't consistent. Like you do one thing and then you do something totally different and it has no relation. And unfortunately, sometimes that comes from some pretty bad experiences in math class, but math is consistent. Ideas transfer, okay? So this concept also works in two dimensions. So I mentioned earlier that a number line is just your one dimension, and when you add the y-axis, that becomes two dimensions. But the idea doesn't change, and that's why the idea is important, that when we're graphing, what we're doing is we're just putting like dots on all the solutions. So we are going to work through an example of this. If you did the summer assignment, which a good number of you did, then you should have, if you genuinely watched the videos, you got a pretty good detailed recap of this particular concept. So when we graph a line, okay, and I think we're going to keep it to lines for the time being, okay, when we graph a line, but keep in mind this would be true for all equations. All we are doing is shading the points that make the equation true, because that's all a graph is. Sorry, that. Okay, because that is all a graph is. It is the picture of all the points that are going to make a particular equation true. Go back. I have like the entire lesson. It's on the PowerPoint, but I also have it in a notebook here. So if you see me keep looking this way, it's because I'm looking at the notes that I wrote down before I put the PowerPoint together. All right, so that's all we're doing. So for example, with the equation y equals 2x minus 1. Okay, so we have the equation y equals 2x minus 1. The point 1, 1 makes this equation true. So in this, if you look at that point, all right, x is equal to 1 and y is also equal to 1. So I'm going to plug that into my equation with the x and the y, and I get 1 equals 2 times 1 minus 1. So y equals 2 minus 1 and 1 equals 1. And I am almost 100% certain that I took too much space up with that. Okay, so I'm going to try to do it a little bit nicer. So 1 equals 2 times 1 minus 1. So there we go. Okay, and of course that is a true statement. And what that means is that 1, 1 is a solution to that equation. So just like you can check your answers to, say, a quadratic equation by plugging the values back in to see if it makes the equation true, it works when you have an x and a y as well, because math is consistent. And so if I were to do the graph for that particular equation, what I would do is I would go over to the point 1, 1. And this is like super hard to do on a computer screen, but I would put a dot at the point 1, 1 because 1, 1 makes that equation true. Okay, don't overthink it. But 1, 1 is not the only point that makes that true. So 2, 3 also makes that particular equation true. So in this particular one point, we have x is equal to 2 and y is equal to 3. So when I go to plug this in, I would have 3 equals, because that's the y value, 2 times 2 minus 1. 2 times 2 is 4, and 4 minus 1 is 3. And so that point also works. So I would come over on my graph or my coordinate plane to the point 2, 3, and I would put my dot there. Now, what we know to be true, though, is that there's actually an infinite number of points that are going to make that particular equation true. It's not just those points. Like, we could keep doing this forever. Now, not every point on the coordinate plane makes it true, but you can, I don't want to get into like subsets of infinity or also infinite. But what we do typically, though, is once we have enough points to see the pattern, we draw a line like so, and we put these arrows on the end of it indicating that that line continues. Now, what we mean by that is that the solutions to this particular equation continue going in this direction. So if you pick any point that is on that black line, whether it's got integers, positives, negatives, decimals, okay, all the little points that are in between the grid lines, all of those points, when you plug them into y equals 2x minus 1 would make that equation true. That's literally all the graph of a line is. It is a picture of all of the sets of ordered pairs that when you plug them into that equation are going to make that equation true. So okay, so I've already managed to mess this up once, so go me. But we're going to take a look at what this does in Desmos. Now, the view that I'm looking at right now, I am able to see the slide that I'm on and the next step, like a slide for what I'm going to see next. Once I go into Desmos, all of that disappears, and what I'm seeing on my laptop completely changes. So I'm going to do my best to try to remember what I put in this PowerPoint, but it's a pretty long PowerPoint, and hopefully I won't mess anything up, but just like your understanding is appreciated. So I'm going to go ahead and I turn off all the other stuff, and now my view of what I'm looking at has completely changed. So we're going to take a look at, in Desmos, the exact same equation that we were just looking at, which was y equals 2x minus 1. And right now I have this so that there's an equation there. On this little, I guess this is like a little gear thing, flower text, I don't know. If I click on that, I have the option to convert this over to a table. And so I'm going to choose that option. I'm going to choose to convert it over to a table. And what's interesting about this is it shows you like these ordered pairs. So down here, these are the two that I plugged in. I plugged in 1, 1, which is right here, and 2, 3. But now you can see that there are more, like 0, -1 works, and whatever this one is, -1, -3, and -2, -5. Now there are infinite number of points though. So suppose I wanted to come over here to x is equal to 5. Well, right now I don't see x is equal to 5. It's running off the screen, but I'm going to delete the -2 and plug in a 5. And I can see that there is a point there, and I can click on the little plus sign there so we can zoom to see it, so it changes our window, but there's the point. If I wanted to, I could plug in 150, okay? So 150, 299 works, and we'll get a very distorted graph. But there it is, okay? So just because you don't see it on the window of the coordinate plane that you have in front of you doesn't mean the point's not there. And what's pretty cool about this, let's see if we can go get something that really messed that up. We could go to -4.5. Okay, and let's zoom that back in. So we're not restricted to just integers, okay? You could have decimals, because every single point on that red line, whether or not you see a dot there at that particular moment, okay? -4.5, there it is down there. It goes with a -10, but would be a solution to that equation. So I could plug in x is -4.5 and y is equal to 10, and I would get a true statement. So I really wanted to take the time that was necessary to emphasize that, because in order for what we're about to do in this lesson to make sense to you, you really need to understand what graphs are. They are the set of ordered pairs that are going to make a particular equation true. And it's not just lines. That's any graph at all, okay? Any graph. So quadratic, absolute value, stuff you've never seen or heard, or like weird stuff, okay? So, and that definition does not change. Oh, and because I messed this slide up before, I have to figure out how to stop the recording. Okay, I think I am figuring this out. If this video comes together and doesn't have a bunch of false starts on it, it's going to be a miracle. Okay, so let's go into a little bit of new vocabulary. It actually might be review from Algebra 1, but we'll assume it's new. We want to define what is a system of equations. So a system of equations is two or more equations that have the same variables in them. So for instance, you might have like 2x plus 3y equals 4, and I don't know, -1/4 x plus 2y equals -6, okay? So that would be two equations, and the variables are x and y. So you wouldn't have x and y in one and y and z in another one, okay? That wouldn't work. And however many equations you have, or variables you have, that's how many equations you need. if you want to be able to solve it. Okay, so that's what a system is, and they can come in all kinds of varieties. Typically in Algebra 1, you are working only with systems that look like this, okay? And so you should, in a good Algebra 1 class, actually learn how to solve systems like this and the different algebraic techniques that are available, okay? So remember, math is consistent. So definitions don't change, okay? Definitions do not change, which is why you need to know them. And it's why your math teacher who's super nerdy keeps going back to the definitions. What is a solution? What is a graph? Because if you really understand what a solution is, it is the value of the variable or values of the variable that make the equation true. And what is a graph? It is the shading in of all of the points that make an equation true. That's what a graph is. If you really understand those topics, then you are able to apply them in new situations. So let's take a look at this. So if we know what a solution is, and we know what a system is, then you can put them together and you can probably figure out what a solution to a system is. Again, it goes back to really knowing what those words mean in the first place. So now that we know that a system of equations is two or more equations, where up until now we've only been working with one equation at a time, and we know the solution is the values of the variables that make the equation true, so let's merge them together. The solution to a system is the values of the variables, okay, that make all the equations true. The definition's built. Now, the reason why we have to we're not changing it, but we just kind of have to like update it a little bit, is instead of values of the variable, now we have to say variables, because now we have more than one variable. So instead of having just an x, now you have an x and a y, okay? So that's the reason why that got pluralized. And then depending on how many equations you have, whatever numbers you come up with have to work for all of the equations. So because there's more than one variable, we have to pluralize this. And because there's more than one equation, we have to make sure that whatever we get works for all of the equations. But it's a very natural extension to the definitions you already know, which is why I harp on those definitions. So let's do some reasoning. This is good for our brains. So we're going to go back and recall those definitions. I know I'm super repetitive on this, and some of you are probably exhausted with it, but they are that important. A graph shows all the points that make an equation true. That's what the first 10 minutes of this video was about. Okay, that's establishing that when we graph a line, what we're looking at are the points that make that equation true. The solution to a system is the values of the variables that make all the equations in the system true. So if the first graph shows all the points that make the first equation true, let yourself think about it for a second. First graph, put the graph there, okay. It's all the points that make the first equation true. And the second graph shows all the points that make the second equation true. How could you identify the solution to the system? By looking at the graphs. So I think, I told you I was going to look over here. I'm going to put a question in the video at this point because I want you to think about this and come up with what you think the solution to the system would be if you look at your graph. Keep in mind what I just put up there. The first graph shows all the points that make the first one true. Second graph shows all the points that make the second one true. And the solution is the points that make all of them true, or in this case, both. Take a moment and reason that one out. So I don't know how it's going to work. It's possible I'm giving you an answer in your formative. Possible. Not going to worry about it. So the answer to that is the solution would be where the graphs intersected. Okay, so the first equation gives you like all the solutions. Well, the first graph gives you the solution to all the first. I can say this right. The first graph shows you all the solutions to the first equation. And the second graph shows you all the solutions to the second equation. So what you're looking for is the solutions that work for both, which would be where the graphs overlap or where they intersect. So let's see this at work in Desmos. And because I managed to mess up pretty much everything earlier on, I have to convert back over to this. Alrighty. So here's Desmos, and we are going to type in the first equation here. So maybe I will, y equals 2x minus 1. Now remember what that is, okay? What we are looking at right here are all of the points that make that equation true. There they all are in all of their decimal glory. That's not even all of them because Desmos has limited, I guess limited precision, how precise it can be. It goes out to 2 decimal places, but really we know that could go out to 3 decimal places or 4 or more, okay? But there they are. There are all the points. So we have the red graph is all the points for the red equation. So now let's type in I guess what will be the blue graph. And what you have here are all of the points that work for the blue graph, okay? It's a different set of points because it is a different equation. And remember what we're looking for. We are looking for the points or the numbers that are going to work for both of those equations. And so if you've got all the red points that work for the red equation and all the blue points that work for the blue equation, then the only point that works for both of those equations is the point 2, 3. That is not what I wanted to have happen. But I don't think I'm going to go back over it. I am going to write on the screen though, and do some notes before I put up whatever's on that screen. So we had the red and we had the blue graph, okay, and they intersected at the point 2, 3. You will often see in your multiple choice answer choice deals, like you'll see the point 2, 3, but you will also see this. You will see x equals 2, y equals 3. So you'll sometimes see it as 2 separate statements, one for the x and one for the y. That is very typical whenever you're dealing with a word problem. So if you have a word problem of some sort where it's not really x and y, but it's, I don't know, sheep and donkeys or adults and kids, so you have some other kind of variables in there, you'll see them listed separately. If you do have other variables and you want to do it in Desmos, you have to change them over to the x and the y. Otherwise, the calculator does not recognize what they were. So I did want to give you that little piece of information. I apparently clicked on the wrong thing. Go me. So why are key concepts so important in math? And you know that in my notes, I'm often like, I'll have a key idea or key concept. Why are they so important? Why are certain things more critical for you than other things? And one of the answers to that is that they enable you to transfer content into new areas without your phone ringing. Actually a math teacher calling me, but she'll understand that I'm in the middle of recording a video. Sorry about that. So they enable you to transfer content into new areas without having to get explicit instruction. Explicit instruction, when something is explicit, it means somebody just tells it to you exactly the way that it is. It means other things that are not math related or education related, but it means that you don't get a specific lesson just on that thing. But if you understand the key concepts, then you're still able to handle that new concept. In other words, you can correctly answer questions that no one has shown you how to answer because the key ideas behind them are ones that you already know. Those key concepts and key ideas just like run through the math. So when you really understand the key concept, you can actually look at an unfamiliar problem, one that no one has taught you how to answer or shown you how to answer, because you already know the key idea or that key concept behind the question that's being asked. So guess what we are about to do? Math is really consistent like that. Okay. And that's why some people seem really intuitive in math. So the teacher asks some question that you've never seen before and you got the kids in the class. Some of you are those kids. Some of you watch those kids. You're like, what? How did they know that? How did they know that? It's probably because they understand the concept underneath it. And it allows them to draw connections between stuff they already know and stuff that is new. So what could you do if the two equations in the system were y equals x squared plus 2x plus 5 and y equals negative 2x squared plus 4x minus 10? So I want you to think about is what is different and then what isn't. So I'm going to pause for a second. I'll let you pause the video if you want to. And I want you to reflect on what about this is something you have not seen before and what about it is something that you've seen before. Okay. So what I hope you came up with is that what's different is that these are not lines, these are quadratics. Okay, so this is what would be called a quadratic system. And so you've got two equations that happen to be quadratics. You could also see one that had a quadratic and a linear, so they wouldn't necessarily have to be the same ones. And then what isn't different, you still have two equations, and those equations are graphable, and they have an x and a y in them. Okay, so none of that has changed. You got two equations, they have x's and y's, and you have the capability of graphing them. What's different is the shape that you're going to get on your screen when you graph them, because they are a different type of equation. Now, up until this point, I don't think anyone has ever taught you how to solve a quadratic system. But I want you to think about what could you do to solve it, given what you already know about graphs, what they are, and about solutions to systems, and what you already know of that. All right, well, I managed to, I don't know what I click on, and clicking ahead in the slideshow and I'm messing it up. And you guys, I don't think can hear it except when I start the recording again. I look like exasperated because I am. I did fix something. I don't know what it was on the previous slide, but this had been a minus sign, and so I am fixing it to be a plus sign. So what we have here is we have our system, and we're going to go ahead and use Desmos to graph it. So we have y equals x squared plus 2x plus 5. Okay, and remember what graphs are. They are the set of ordered pairs that will make that equation true. So if I take that equation and I plug in negative 2.78 for x and 7.168 for y, I will get a true statement. I don't want to plug those numbers in because those are terrible numbers, but that's, I would get a true statement. And there are an infinite number of solutions, and there they all are. Now let's take a look at the next one. So y equals negative 2x squared plus 4x, and it should be plus 10, and it might have been minus 10 on the previous slide. I'm sorry. Okay, and now what we have there is we have a separate graph for all of the points that make the purple equation true. Now, Desmos is smart, but stupid. Desmos can do a lot of amazing things, but it can't read your mind and it doesn't know what you're trying to do. And that's where you need to understand the math yourself. It's like Desmos is a tool, but it doesn't do math for you unless you know what to tell it to do and what you're looking for. So Desmos gives you a whole bunch of dots, okay? Like a bunch of dots, a dot anywhere that like it thinks might be of interest to you, like the vertex, okay? But remember what you're looking for. You are looking for the values of the variables, in this case, x and y, that are going to make both equations true. So just like with lines, you're looking for the point of intersection. It doesn't matter what the shape is. You're looking for the point of intersection because none of the rest of that has changed. Now, there are actually 2 points of intersection on these two, and don't get distracted by other points or dots on there. This particular system actually has 2 solutions. One of them is awful, but we have -1, 4, and we have 1.667 and 11.111. Now, a couple of things. When you see them listed, like I mentioned earlier, you could see like x equals y equals. Because there's more than one, you have to make sure that you're pairing it together the right way. So if you were to list them, you would have to say something like x equals -1, comma, y equals 4, and then you would have to list the other one separately. Okay, y equals 11.111. You couldn't do x equals 1, x equals 1.667, y equals someplace else. You have to have them paired together, okay, as like the pair, because they come in a pair. Okay. The other thing that you might notice is that Desmos is going to give you those values as decimals. And I know, like, just right off the top of my head, that 1.667 is 1 2/3. And so this would probably show up as 5/3 in an answer choice bank. What you would need to do if you got answers in decimals and then you look at your answer choice bank and their fractions is you want to grab your calculator and just do the division out. So you might see oh, it's not going to let me do it unless I turn the pen off. So you might do something like this, just do 5 divided by 3, and you can see, oh, okay, that's where that 1.667 and so you could work it out that way, okay, and kind of match the fractions up with the decimals. All right, so that's how you can do a quadratic system in Desmos. I'm rolling my eyes at myself for clicking on wrong things. Okay, so let's look at another one. Now this one, when you look at it, we have an x to the third. Now we have not covered x to the third, okay? Have not covered it. You don't, you might be surprised when we go to graph it because you're like, I don't know what the shape of that graph, like what is the pattern for the points on that one. And then we have what you should recognize as a line, okay? Now, I haven't taught you explicitly what to do if you have a system like this, but you know that the graph of the first one is going to show you all the ordered pairs that make that particular equation true, because that's what a graph is. That's the definition of graph. And you know the second graph is going to show you the same thing for the second graph, and you know what you're looking for if you're looking for the solution. You're looking for the ones that work for both. So there's no reason why, even if the look of the equations has changed, why the process for solving it should change. So let's do it. So y equals x to the third minus 4x. Okay, so you might be surprised if you've never seen that before, but reiterating, repeat, all those ordered pairs, if you were to plug them into the equation, would make the equation true, because that's what a graph is, and that's why you need to know the key ideas. And then our second graph here is going to be y equals x minus 3. And again, remember, Desmos is smart but stupid, and it doesn't know what you're trying to do when you're graphing these, but we know that you are looking for the points where the graphs intersect. So we have that lovely point, this lovely point, and this one right here. Now, those have awful answers because there's no rule that says you only ever deal with nice numbers in math. A lot of times teachers will try to make the numbers nice for you, but that's because we're nice people and we try to make the numbers nice. Real life does not do that to you. Real life will throw you whatever numbers happen to come out. But if you were doing this problem for an exam, and remember, even though you don't have Desmos on your SAT, you are allowed to use a graphing calculator. Now, they work differently. You would need to take the time to learn how to use it, but a graphing calculator would do all of this as well. Okay, and don't be distracted just because Desmos put some other points on there. Okay, so it doesn't know. It thinks maybe you want the y-intercept, which is 0, -3. So it puts a dot there. Maybe you want the x-intercept, which is 3, 0. If I click the red graph, like maybe you want that point where it turns around. Okay, so just don't get distracted by extra points. Know the points that you're looking for your particular answer. Right, I have to stop the recording again. Maybe I can make it through the end of this presentation without any more PowerPoint snafus, but I don't think that's realistic. Just don't think that's a realistic thing. So what if we had more than 2 equations? If you go back in this video to the definition of a system, it says 2 or more equations with the same variables. And so far we've looked at ones that just have 2 equations, but we know that that definition opens us up for possibly having more than 2. Full disclosure, I think the biggest system I've ever had to actually solve was 7. And it was for an applied mechanics class that I took in college. And it was an awful problem. And I absolutely used technology to do it. I did not try to do it by hand. But I had a graphing calculator, and the graphing calculator had an app or program on it that would do it. It had to do with a volleyball net on a beach. It was awful. Okay, now typically at the high school level, these would be linear equations in 3 dimensions. Okay, so they're not quadratics, they're linear, and they are in 3 dimensions. I don't think I ever had to solve anything worse than that when I was in high school, and I can't imagine that you would. In fact, the way the actual like real life works, you really wouldn't see, like they would all be linear. They can get to more than 3 dimensions, but I've never seen systems like of like 7 quadratics or anything like that. I've just never seen anything like that. So I don't lose any sleep over it. Now, they would, and I love typos so much. I love them when I get into a video and realize I have a typo. They would have an X, Y, and Z coordinate. So you know that we live in a 3-dimensional world. So these actually can be graphed, but you would need some kind of like 3D graphing software or something. But you got your X-axis, you got your Y-axis, okay? And then your Z-axis is like it comes out of the page. If you look at a corner, so I'm like looking up the corner of my living room, okay? You can actually see like where the ceiling meets the wall. Okay, assuming you don't have like an arch ceiling or something, but you can see the 3 straight lines all coming in at that one point. That would be the origin. And think of the vertical for your wall is your Y. One of the ceiling lines is an X, and then the other one's coming out at you. And so they would have an X, a Y, and a Z coordinate. But the definition of what you are looking for does not change, which again is why it is so critical that you know those definitions and you're not just copying problems trying to get answers, that you really know what you're looking for. So what are we looking for in this case? You would want the variables of the values of x, y, and z that make all three equations true in this case. If you had x, y, z, and usually would add a w. If there was a fourth one, it would be like you'd have four equations. Okay. So you would want to be able to plug in the x, the y, the z, and then it would make all three of the equations true. And that hasn't changed. So just like the solution to one equation, like you plug in the value for x, you evaluate it, you get a true statement, you know that that's a solution. Okay. If you have a system of two equations, you have the x and the y that make them both true. And then if you have three, it just extends out. It's the same idea, just moving into three dimensions. Desmos does do this, but it requires some instructions. So pay careful attention to this next part. You might even want to have Desmos up on your phone or on another window to just kind of follow along and do this. I'm actually pretty new at this as well, so hopefully I'll be able to demonstrate it okay. My expectations are kind of low at this point, but you know, I did do it when I was practicing before I recorded this, so in theory it should work. So let's take a look at this. So I have three equations there. I have 2x plus 3y plus z equals 4, 2x plus 3y minus z equals 8, and negative x plus y minus 2z equals 1. And what I'm looking for are the values of x, y, and z that when I plug them into the first equation, I will get a true equation. I'll get a true statement. I'll plug them into the second equation and I'll get a true statement. And I'll plug them into the third equation and I'll get a true statement. They have to work for all three because that is the definition of a solution. So let's take a look at how this is done. Okay, so this does require you to pay attention. So what I do is I'm going to type in the first equation. So 2x plus 3y plus z equals 4. Now, why it's not doing it, so you got this like exclamation point, okay? Too many variables, try defining z. And so what is happening here is Desmos is written to work in two dimensions. It's got an x and a y. So the moment you type a z, it does not understand what z is. Okay, it just doesn't understand what that is. So we are going to add something called a slider. All right. So now what it does is it graphs 2x plus 3y equals 4. And it substitutes in right now, z is equal to 1. Okay. And graphs that. Okay. So just kind of keep that in mind. Now we're going to type in the second equation. 2x plus 3y minus z equals 8. Notice it doesn't error on me at this point because it's assuming z is equal to 1 because we have that slider there. Okay, that says z is equal to 1. I could change it. I can move it like over here. Okay, or over here, and you're just like plugging in different things for the z value. All right, and now we're going to graph the third one, which is negative x plus y minus 2z equals 1. Okay, so now we've got all three of the equations on here. As it is, okay, if z is equal to, oops, that's not what I wanted to do. There we go. I don't want to animate anything. No animations. Okay. Add the slider. There we go. Okay, it's back. Now, when z is equal to 1, you notice that you got the purple line here and it's intersecting the green and the red. But remember what we're trying to do? We're trying to find the values that work for all three. So what I do is I take the slider and I'm just going to slide it until I find the Z value that works for all of them. So kind of watch this. I'm just sliding it back and forth. Notice how as I get closer to Z equals -2, all 3 lines have converged in one spot. And what that tells me is Z equals -2 is the value of Z that's going to work for all of them. And if I can click over here and find the coordinates of that point, I have the point 30, and here is my answer. Okay, so the answer would be of the form x, y, z. I know x is equal to 3, y is equal to 0, and from my slider, z is equal to -2. You might also see just this, x is equal to 3, y is equal to 0, z is equal to -2. Okay, or you could see it as what's called like an ordered triple. Triple for 3. Ordered because it goes X, Y, and then Z. Okay, so the way that you do that in Desmos is you type in all 3 of your equations and then you add a slider for the Z. And then you move the slider until you get all 3 lines to converge on a single point. And that point will give you the X and the Y, and then the value on the slider for Z will give you the Z value. So you might want to rewind that and watch me do it again, because you are going to have to do one in Desmos on your own and see how it goes. Okay, it's pretty cool, and it's actually a really efficient way to do a problem like that, because the algebraic way is actually pretty awful. It's pretty involved. All right. So now for the biggest secret ever. Most of you are going to disagree. You're going to be like, I don't know if it's the biggest secret ever, but it's a pretty big secret, okay? And it's also really, really powerful. And we're all about powerful concepts. You can solve any equation by using systems of equations. I'm going to let that as a pretty big secret sink in for a second there. Yep, you can solve any equation by using a system. So, and that includes all kinds of stuff that you have never seen before or know what those equations are. So suppose you saw that beautiful equation, okay? There is nothing beautiful about that. That is pretty horrible. And now we're getting into stuff that I actually didn't try. I have the answers to these ones, but I didn't try them out on mine. So I'm just gonna see what is life without some adventure, right? Okay. So you know what you're looking for. You're looking for the value of x that when you plug it in here, 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 and here, and you do all your order of operations, is going to give you a true statement, because that's the definition of a solution to an equation. It's the value of the variable that makes the equation true. The problem with this equation is that you haven't been taught how to do the mechanics. Like, what do you need to do in order to get x by itself? And I'll give you a hint, it's not fun. All right. So these equations are not fun at all. So how can you use what we just covered about systems of equations to figure out the answer to this? We want to know which values of x will make the left side equal to the right side. Okay, there's that definition again, that definition of a solution. You are asked to solve something, and so this is what you're looking for. I want to know what's going to make this left side equal to the right side. That's what I'm looking for. So we are going to make the left side into its own equation. We're going to say y equals, and then we're going to type in the whole left side. and make the right side into an equation. So we're going to say y equals, and then we're going to type in the right side. So what we're going to do is turn this into two separate equations, one equation for the left and one equation for the right, and see where they intersect, because that's what we're looking for. We're looking to see when they would be equal to each other, and where they're equal to each other is going to be where the graphs intersect. The x value of the point is the solution. So the only thing that's a little bit different about this is when you get it off the graph, you only actually need the x value because there's only an x in the problem. The y value is something we're going to put in order to change it into a system so we can graph it, but we don't need the y value. We are only going to be taking the x value because the x value is what we're looking for. Okay, so let's do this. It's a pretty big secret. So what I'm going to do is take the left side of that equation and turn it into its own equation. So I'll do y equals. Now, getting the fractions in Desmos, I think I need to put the x plus 6 in parentheses so that when I hit the division symbol, it's going to put the whole x plus 6 in there. I think if I don't put it in parentheses and I just do x plus 6 and then do divided, it only puts the fraction bar under the 6. So you do need to type in parentheses and then the division, and that'll be 4x squared plus 3 over 2x squared. Okay, now it doesn't matter that you have never seen this kind of a graph before. Okay, it doesn't matter because you know what that graph is. That graph is all the values of x and y that if you plug them into that equation are going to make that equation true. It was just really nice of Desmos to do it for you. Okay. Second one will be the right side of the equation. So we'll do y equals, and then again, I do need those parentheses around that numerator just to make sure that the fraction bar gets placed correctly. Okay, and now what we're looking for is where they intersect. This is a bit of a tricky one to see. I'm going to zoom out a little bit so you can kind of see what's happening. It actually just looks like the blue is overwhelming the red. What we're looking is for where they intersect. So what I hope you can see is that the, well, no, we haven't talked about asymptotes. What I hope you can see is that over here is where they intersect. And Desmos was super nice and put a point there for us because Desmos understands that that's a point we might be interested in. If I zoom out, Desmos is not putting like other points on there. Now I see a couple points over there. I could try zooming in to see what was happening over there. And you can tell right there, it looks like that's just an x-intercept. It's obviously not where they're intersecting. But right there, that point is not an x-intercept. That's where they're intersecting. And so the answer to that equation is x equals, because remember there's x in the equation. We don't have to worry about the 0.25. Okay, 0.25, you don't need to worry about it because x is the only thing we're worried about. X is equal to 4. And that actually is the answer. That I had written down. So x is the x equals 4 is the answer. That's where they intersect. And so that's how you could solve anything. So it doesn't matter how awful the problem is. Okay, doesn't matter how awful. Now, just before we click off, because I know I'm right near the end of this PowerPoint, like I'm super close. One of the problems that I have slated for you to do in Desmos. Oh, no, I don't know where it is. Oh, well, you would have already seen it. So, well, somebody will ask me if they get stuck. Well, maybe not. If you need to do a sine wave, and I think it's y equals sine, and it says sin, you can just type that in and it'll work. Okay, just if you got stuck on that one. Okay. So yeah, we're right at the end here. So before concluding, there are 3 more questions in formative. I don't exactly know how that's going to work. I'm going to do something that I've never done before with assigning the formative questions. So I'm hoping that it works out. So you'll probably see those right about here. And then the final assessment, if this is how I want you to think about this. If the first 10 questions in formative were classwork, okay, consider the last 5 as homework. And the way I want this to work is this is like a lesson that you would sit in class, you watch, you take some notes, you get those definitions, you do some practice work, you submit it, and then I give you 5 problems to do at home. Okay, that's what the last 5 in the formative are. The assignment is due before 11:15, and I am going to be in a totally different time zone. I hope. If I'm not, it means I'm home super sick or something instead of being in a different time zone. So let's hope that that's not the case. But it could be one or the other. But you can try to message me if you want. I just can't guarantee you like a response when you want it. Okay. So there we go. So there is our first independent lesson. You guys know where and how to find me. If you have questions, I will do my best to get back to you.